All right, everybody, let's go ahead and continue with the final test for two means. So this last topic deals with considering values, quantitative values that are paired. Therefore, this is known as the paired t-test. And what we mean by paired is that whoever is in group one is somehow tied to group two. So let's say that you're looking at reaction time. So the random variable of interest here is how quickly we react to something. In this scenario, I'm going to assume that it's based on driving. So for example, if something shows up on the road, can you avoid it? Something along those lines. So the random variable of interest here is reaction time. So therefore, we can see that there is this variable y that we're going to go ahead and measure. Now, there is a factor here, which is the number of beers. And so here we basically have no beers. So this is someone who did not have a beer. And then there's someone who did have a beer, or really, I guess, two beers, because two is better than one. So if you're looking at the reaction time and you believe that the factor beer or no beer is important, then you're interested in reaction time. And previously, we've seen that this could be in dependent samples. If, for example, you took a group of 100 individuals, and then you went ahead and randomly assigned 50 individuals to the no beer, so they're sad drivers, and then you have 50 individuals in the yes beer. So in this case, this would be independent samples because you just simply have an individual in population one that is completely independent, different from individual in group two. Now, that would change if, for example, which is what they do here, you recognize that there's a lot of difference. There's a lot of variability in someone's reaction time. So some people react a lot faster than others, and that's just natural variability. So you could go ahead and say, well, if I select a driver here and this person is a slow react, like for whatever reason, they're fairly slow at reacting. And then, for example, you get a person over here that's very fast at reacting, right? Because they're just very fast. Then it doesn't really make a lot of sense for you to consider these guys separately. And so a better design to see the impact of beer, no beer. So you pair to basically try to control external factors as best as possible. Marker's not working. And this is why twins are perfect for a lot of pairing or using the same individual. So to control for external factors as best as possible, what should actually happen is those 100 individuals should all participate in group one and also in group two. So all of them can, for example, you want to randomize this also so they don't all start with the sober driving. So maybe 50 of them start with sober driving, 50 of them start with drinking and then driving. And then you shuffle them and they try this again. So in other words, a person that participates here would then also participate after having a few drinks. And that way, if this person is slow, then you expect them to also be slow over here. And vice versa. If they were very fast to react, then this person here, you expect them to also be fast. This assumes that there is no difference with that treatment there. So what we recognize is that there is this pairing where, for example, a slow person would be slow in both cases. And so this should really detect whether the treatment or this intervention, the beer, had any effect on their reaction time. And somebody that is fast would also presumably be fast after drinking the beer. So this helps you to, in essence, control for that variability from reaction time from individual to individual. And what we do here is that you recognize that whoever is in population one is intrinsically tied to people in population two, drivers who had two beers. And that right there results in a pair t-test. So again, pairing is ideal for controlling as many variables as possible. And that's why twins are perfect for pair t-test. Now, this is actually pretty easy because what ends up happening is you say we do have two separate values. Like, for example, here would be the reaction time for person one. Here would be the reaction time after they have a couple beers. And then you do that for every single person. You're not really interested in the reaction time per se. What you're interested in is the differences, right? I don't really care what the reaction time was when they did not have a beer. I really care about the difference. In other words, is there a non-zero difference in this reaction time? So if you subtract these values, so if value number one and value number two are roughly the same, then this difference, the DI, should be approximately zero for person one, person two, person three, person four. That is, it should be zero. That's my null hypothesis, unless there really is a difference in reaction time from these two different groups. So once you go ahead and recognize that there's a pairing of individuals in group one to group two, you're really going to go ahead and just simply take a step back and say, well, it's not the values that we're interested in, it's the differences. And so these differences are your true data. That's what you're really going to perform a hypothesis test on. So let's just go ahead and visualize this. Once you recognize that you have the true data being the differences, this becomes a one sample t-test. And that's pretty much it. So let's go ahead and take a look here. Example 0 starts by saying a psychologist student wants to test whether drinking a cup of coffee improves reaction time. So again, we're kind of changing from the example we opened with. Here we were talking about beer and reaction time. Here now we believe that if you start your day with coffee, then if you drink coffee, then your reaction time should improve. And remember, that means that you react a lot faster. We've already talked about some people reacting much faster than others. I think my natural speech rate is pretty fast, and some people don't like that. And so I think maybe if I have coffee or beer, it could, again, should be close to that rate of speech. So here you can go ahead and notice that they only take 6 individuals, and you're going to test the reaction time before they drink coffee and then after they drink coffee. And it's not the values that we want. For example, here's someone that has a reaction time of 260 before, and then here's someone that has a reaction time of 225 before. And so if you shuffle these and you just compute the mean in group one, that really wouldn't matter. But you recognize that this person has a slowish reaction time, 260. This is in milliseconds. And so their reaction time afterwards, it's comparable. It's around 240. And you see that more or less holds in all of these cases, 245 and 230, 275 and 260. Now we take a look at 6. This person is fairly quick, 225 versus 220. And you can see that the reaction time did improve a little bit, but they're very fast before and after. So this helps to control for that person-to-person or subject-to-subject variability. And remember that really what we're interested in is the difference. So let's go ahead and recognize that before we can call this group 1, and the after we can call group 2. And what we're going to do is we're going to go ahead and compute the difference in group 1 from group. Really, it should be the difference from group 2 to group 1. So group 1 is called the xi, group 2 is called the yi, and the difference is going to be di. So the difference in group I, by this formula, it's xi minus yi. So group 1 and then minus group 2. So 260 minus 240, that's 20. 245 minus 230, that is 15, and so on. So go ahead and find all of these differences here. And once you get the differences, you have the sample. All right, so here we have our differences already computed. And what I want to point out is, again, that this becomes your actual data set now. And it's just going to be a one sample t-test. So let's highlight these differences because this is going to be your data from here on out. And we'll perform a complete hypothesis test on these. Before doing that, I do want to point out that you see that the first difference is 20, right? We see that here. And the fact that 20 is positive means that the first value, so if this is positive, that means that the first value is larger. And notice that for most of these are positive, which means that the reaction time was longer. So positive difference indicates longer reaction, in other words, slower in group 1. If you have a negative, then that indicates that there's a longer reaction time in group 2. And that only happens once right here. So individual number 5 took 245 seconds before they drank coffee, and then they took 250 seconds after they took coffee. So the sign of the difference, because you're taking group 1 and subtracting by group 2, whatever the sign is on the difference, so if your difference is positive, that means that this guy right here, the first value is larger. If your difference is negative, then that tells you the second one is larger. So overall, we can see that the first value tends, there is a tendency here for the first value to be larger, which means that they take longer to react. A tendency. And so this, now that we've got our true sample, you can see how it's very natural to write the null hypothesis. It's always going to be that the mean difference. So the true mean difference, pair difference, is going to be denoted by mu because it's the population value. And then we're going to use Greek letter D, delta. So mu sub D is 0. Okay, and the reason for that is that we're interested in the paired differences. So if the difference 1 is x1 minus y1, then we're really trying to make a claim regarding that difference. So my hypothesis will always be that the mean difference, the population of differences, is 0. Let me use a different color so we can see this a bit better. All right, so there we go. Now, this student, remember that the way that we got the differences is it's always group 1 minus group 2. So it's always group 1 minus group 2. And you need to know that because now we're going to ask, what should the alternative be? So what symbol do we use for the alternative? And so that's always up to you. So a psychology student wants to test whether drinking cups of coffee improves reaction time. So now you need to really use your subject matter expertise here and say, well, what does that mean? So the claim is that drinking a cup of coffee improves reaction time. So I always like to ask which of these times should be larger than. So if you can identify which one is larger, so would the time to react be larger before, or would it be larger after? And after some thought, you recognize that if coffee improves, then that means that time before should be greater, right? Should take longer than time after drinking. Because the time after drinking, it should speed things up. And remember, the time before was group 1. So here we have a greater than symbol. So 1 is greater than, remember that if it's if reaction time 1 is larger, then your differences should be positive. So that's why we're going to say that the population of the differences, the mean of the differences, should be greater than 0. And that's pretty much it. We've got our hypothesis, and because we have a lot of experience with the one sample t-test, I'm just going to go ahead and specify this, that we need to assume that you have a simple random sample, you have independence, but really here it's of the differences. And so then you need to check whether the sample is greater than or equal to 30, or the population is normal. And remember, it's for the differences. So I've got the differences in here. Let's go ahead and verify the requirements. So it's safe to assume that we have a simple random sample. Safe to assume that they're independent. It's not safe to assume that, we have the shape requirement met. And here we only have 6. That's clearly not big enough. So we're going to have to check whether the population is normal. And remember that the population is this differences here. All right, so I have my data here. If you want to compute the differences, it's fairly easy. You go to data, compute expression, and you remember that it's simply group 1, which was before, and I'm going to go ahead and subtract that by group 2, the after. And notice how we've got the same values, 20, 15, 15, 10, 20, 15, 15, 10, -5, and +5. So here are the differences. This is your population now. So you're going to essentially ignore this before and after. So now that I've got these, I want to ask, is there evidence to say that these are normal? So we're going to create a box plot, look at the differences, and you can see that I don't like that there's this skewness going on, but again, it's not substantial enough to see any outliers. So no outliers present. Let's go ahead and make a QQ plot. All right, and so there's my QQ plot. Again, I also don't like this value, but other than that, we got a pretty high correlation coefficient, 0.962. So we're just going to go ahead and proceed. So box plot shows no outlier. And R was 0.96 something. 62. All right, so we're going to go ahead and proceed. So we got our hypothesis. We verified that the conditions are met. So now we're going to go ahead and proceed. Remember, this is a one sample t-test. So that means that my distribution here, because n is 6, is going to be a t-distribution. And I'm performing a right tail test. So the area on the right, there's no alpha given. So we'll default 2.05. Degrees of freedom is 5. And we can go ahead and find the critical value here. All right, so if we find the critical value, we can then go ahead and compare that to my test statistic. And the test statistic is T. And remember that it was always the mean difference, so D bar, over the standard deviation of the differences over square root of n. I'm not going to use, I'm not going to do this by hand. I'll simply use StatCrunch. So let's go ahead and try this. This is a one sample t-test now. So let's go, remember that your real population is this now. So we'll go to stats, t-stats, one sample with data. Click before and after. And my hypothesis is a right tail test. So mu greater than 0. I can also go ahead and show the critical value here. So let's try this. So my critical t value is 2.015. And my t statistic, you can see degrees of freedom and standard error. So that's the SD over square root of n is 3.65. And therefore, plugging everything in with your sample mean. So these are the values that you need. So it's sample mean over this quantity. Gives you 2.75. So 2.75 is my test statistic. And remember that test statistic of 2.7 means that we land right here. Our sample lands in the critical region. So we reject the null hypothesis. That means there is evidence to support the alternative at the 5% significance level. So it looks like, yes, we were correct that reaction time does tend to improve after drinking coffee. And we saw that initially in our sample because of all of the tend for the differences to be positive. And that more or less wraps it up. So let's just wrap up by writing down the p-value, and then I'll make a final note. So remember, the p-value is just the probability of getting a more extreme value. So from your test statistic outward. And we see that it's 0.02. So that's definitely smaller than 0.05. So here is a full pair t-test. Because we're using StatCrunch, it's actually way easier to do this. I actually computed the differences by hand or with the command. Let's say I did not do that. So here, let me pretend that this is not our first example and that you're just saying, hey, we're doing another, like, let's start here. And you know that it's paired. You write the hypothesis. So basically you write down the stuff in orange and then we'll do the stuff in blue. So here you go to stats, t-stats. And because you have two samples, you feel that you got to go to two samples. But notice there's this sample, there's this third command called paired. Select paired. And then it just tells you what is sample one. Please make sure that you keep the order the same as your paper. So whenever there's two groups, we're used to labeling group one and group two. So here we're going to label the before group one. The after is going to be group two. And that's about it. You can go ahead and save the differences. And then here you're performing a hypothesis test for the mean difference. So they use capital D rather than Greek D. We're always going to leave this at 0 for our class. And then we'll select the appropriate alternative hypothesis. And we can get more or less the same results as that one sample t-test. Same p-value, 0.0204. Same t-statistic, 2.738. Why is that a 5? I hope I miswrote that. But everything else is the same. So we can see that the mean is the same and the standard error is the same, 3.65, giving you the t-statistic. Critical t-value, 2.015, 2.015. So we get the exact same critical value, exact same test statistics, which means that we will get the same conclusion. So this is how StatCrunch would make these tests very simple for us. So please just make sure that for this one, you look at the differences. All right, thanks for joining me. In the next video, we'll do another example.